Welcome to the introduction, the stillness of the variable, a gentle sanctuary where your mind can finally rest. As we begin this journey, simply allow yourself to be present in this exact moment. Feel the weight of your body settling into the surface beneath you. Take a slow, deep breath in, drawing the cool air through your nose, filling your lungs with a sense of peace. Now, release that breath slowly, letting go of any tension you might be holding. There is nowhere else you need to be right now. There is nothing else you need to do, just breathe. With every exhalation, you sink a little deeper into comfort. Imagine the muscles in your shoulders softening, melting downward as gravity holds you safely. The world outside this room is fading away, leaving only the steady rhythm of your breathing. Inhale again, counting slowly to 4, and exhale deeply, letting the air flow out completely. This predictable cycle of breath is like a steady constant in an always changing universe. It is a reliable rhythm that anchors your physical form, preparing your waking mind to softly drift into the beautiful, structured calm of pure, quiet thought and deep resting sleep. Tonight, we will explore a tranquil realm where logic meets serenity. We will wander through the gentle landscapes of mathematics, a place where absolute stillness and perpetual motion coexist in perfect harmony. Mathematics is often misunderstood as a rigid language of stress or strict calculation, but at its very core, it is simply the poetic observation of patterns and truths. It is a very calm space where everything eventually resolves, where questions always find their peaceful answers. Allow your mind to become entirely open, receiving these concepts not as complex problems to solve, but as beautiful artistic landscapes to observe. Let us begin with the fundamental idea of the variable. In the quiet language of mathematics, a variable is not a source of confusion. Rather, it is a symbol of endless potential. It is an empty vessel, calmly waiting to hold meaning. Think of a variable as a gently resting leaf on a completely still pond. It does not demand attention, nor does it force a specific outcome. It simply exists, holding space. It represents an unknown value, but the unknown does not need to be frightening. Here, the unknown is simply a quiet possibility, resting in pure absolute peace. Picture this variable in your mind as a soft, glowing letter hovering in a vast, dark expanse. It might be an X, or a Y, or a Z. It spins so slowly, shedding a faint, warm light into the surrounding void. This letter does not have a fixed identity yet. It is completely free from the burden of being a definite number. While the number 5 must always be exactly 5, the variable can be anything it wishes to be. It possesses the incredible freedom of continuous transformation, yet it remains perfectly still in its current, deeply relaxed, undefined state. As you watch this glowing symbol, take another deep breath in, letting your lungs expand fully. Hold the breath for just a fleeting second, embracing the pause. Then gently exhale, feeling an even deeper wave of relaxation wash over your limbs. Just like that momentary pause between your inhalation and your exhalation, the variable represents a threshold. It is the very doorway between what is known and what is yet to be discovered. It stands calmly on the border of change, never rushing, never forcing the mathematical equation to move faster than it naturally should. It is always entirely patient. Consider the concept of persistence in mathematics. We often refer to these unchanging values as constants. A constant is a number that stays exactly the same, no matter what happens around it. It is like the solid, immovable bedrock at the bottom of a gently flowing river. The water above it may rush, swirl, and change its pace, but the bedrock remains steadfast and secure. In your own life, and in your own mind, there are constants too. Deep inside, there is a quiet core of pure peace that remains unchanged, no matter how fast the world moves around you. When a variable and a constant meet in an equation, they create a beautiful balance. The constant provides a steady anchor, while the variable introduces the gentle possibility of change. This relationship is the very foundation of how we describe motion in our universe. Without the constant, everything would be chaotic and untethered. Without the variable, everything would be entirely frozen in place. Together, they allow for a smooth, predictable flow. As you breathe gently in and out, recognize this same delicate balance within your own resting body. Your steady heartbeat is your constant, grounding your freely flowing thoughts completely. Imagine now that you are tracing a line on a massive, softly illuminated graph. This graph exists in a boundless space of deep blue and purple hues, resembling the twilight sky just before the stars appear. The horizontal axis stretches endlessly left and right, representing time. It moves at a constant, unhurried pace, ticking forward like the calm rhythm of a grandfather clock. The vertical axis reaches up and down, representing the variable. As time marches slowly forward, the variable gently rises and falls, drawing a smooth, elegant wave across the dark canvas of your deeply relaxed, perfectly peaceful mind. This elegant wave is the physical shape of change. Notice how there are no sharp edges, no sudden drops, and no erratic jumps. It is a continuous, unbroken line, flowing seamlessly from one point to the next. In the language of calculus, we call this a continuous function. It means that to get from one resting place to another, the line must peacefully travel through every single point in between. There are no skipped steps, no rushed transitions. Every single value is calmly acknowledged and gently passed through. You too can transition into sleep with this same unbroken, soothing smoothness. At the very crest of this elegant wave, there is a singular, magical point. For a microscopic fraction of a second, the line stops rising, and it has not yet begun to fall. In this infinitely small fragment of time, the variable achieves absolute stillness. The mathematics of motion reveals a profound secret here. At the peak of all change, there is always a moment of complete and total rest. Breathe in deeply as you imagine reaching the peak of that gentle wave. You are resting at the summit, suspended in a weightless state of perfectly pure, quiet, deep tranquility. As you slowly exhale, the variable begins its gentle descent. It glides downward, mirroring the release of air from your chest. You are descending with it, drifting further away from the active thoughts of the day. The variable does not resist this downward motion. It does not cling to the peak. It understands that falling is simply another form of changing, a necessary return to the baseline. Allow your own mind to softly fall with it, sinking deeper into your mattress, feeling heavier, feeling warmer, and letting go of any lingering desire to control the unfolding events of tomorrow entirely. Now consider the spaces between the numbers. If you take the number 1 and the number 2, there is a quiet space between them. We can divide this space into fractions, creating smaller and smaller pieces. A half, a quarter, an eighth, a 16th. No matter how many times we divide this space, we never truly run out of room. The variable can slide effortlessly into these infinitesimal gaps. In mathematics, infinity is not always a massive, sprawling expanse. Sometimes, infinity is comfortably folded into the tiny, quiet spaces between two simple numbers, resting securely, entirely undisturbed, and perfectly still. As you visualize these infinite, tiny spaces, let your breathing match their subtlety. Notice how every single breath you take is entirely unique. Like a variable, your breath changes its volume, its depth, and its pace. Yet, the underlying purpose of the breath remains constantly steadfast. It nourishes your resting body. It oxygenates your deeply calm mind. Focus closely on the soothing sensation of the air entering your nostrils, cool and refreshing, and exiting pleasantly warm. You are absorbing the calm stillness of mathematics, incorporating its logical serenity into every single deeply relaxed muscle fiber within your entire physical body. We are about to step further into this abstract world of equations, moving from simple constants to graceful curves of motion. But for now, just linger in the introduction. The variable remains quiet, a beautiful silhouette resting against the twilight grid. Your mind is perfectly prepared, wonderfully relaxed, and deeply grounded. There is no test to pass here, no final answer to find. There is only the harmonious observation of changing values finding their ultimate equilibrium. Close your eyes deeper, breathe, and let the gentle logic of the mathematical universe carry you safely into restorative, profoundly peaceful, deep healing sleep. Chapter 1, The Foundations of Accumulation, begins in the quiet spaces between numbers, where discrete moments blur into a continuous stream. This is the profound mathematical realm of the integral. Imagine a single point, holding still in the vast expanse of your mind. As time gently pushes this point forward, it leaves a delicate trace, a fine line drawn across the emptiness. When this line begins to sweep sideways, it creates an area, slowly gathering space within its boundaries. This steady, inevitable collection of infinitesimally small fragments is the pure essence of integration, a calm pooling of mathematical truth. We are not rushing to find an answer today. We are simply observing the flow of quantities as they pool together like water filling a quiet, stone basin. The symbol of the integral, that tall, elegant, curving shape, resembles a gentle wave standing completely still in time. It gently invites us to look beneath the shimmering surface of the function. Beneath this surface, we find the accumulated history of a changing rate, a beautiful story told entirely in the soft language of infinitesimals. To deeply understand this story, we must return to the foundational techniques of our deep mathematical past. These techniques are not rigid rules, but fluid motions, much like the rhythmic breathing of the ocean tide. We will breathe in the immense complexity of the integrand, and we will exhale the pure simplicity of the antiderivative. Let your mind settle deeply into this calming rhythm. There is absolutely no urgency here, only the steady, methodical unpacking of mathematical truth. The sturdy foundations of accumulation rest upon our unique ability to perceive hidden patterns, to recognize the faded ghosts of derivatives past, and to gently, carefully reverse the relentless forward flow of continuous mathematical change and passing time. The most fundamental of these gentle motions is substitution, a process of deep simplification that echoes the chain rule of differentiation. Imagine a complex expression as a nesting of shapes, one hidden carefully inside another, like smooth pebbles resting peacefully in a rushing river. When you look closely at the clear water, you might notice that the circular movement of a larger eddy is perfectly mirrored by a smaller swirl nearby. In the landscape of calculus, this beautifully happens when we see an inner function and, resting quietly beside it, the exact derivative of that very same inner mathematical function. They are intimately linked, securely bound together by the long history of the chain rule. To integrate this, we perform a gentle shift in our perspective. We simply define a new variable, universally called u, and we let it absorb all the inner complexity. This single u becomes our new reality, our new clarifying lens. As we establish u, we must also carefully transform the infinitesimal differential, the dx, into a brand new differential, the do. This profound transformation is never arbitrary. It is a highly precise scaling, strictly governed by the known derivative of our newly chosen variable u. We patiently watch as the complex integrand dissolves, its jagged edges softening as the inner function and its derivative merge into the simple variable u and its differential do. The complicated nesting disappears, leaving only a pure, elementary function in its tranquil place. We then integrate this simple function with incredible ease, like effortlessly stepping across a calm, shallow stream. The antiderivative smoothly emerges in terms of u, perfectly whole and resolved. But the mathematical journey is not quite complete. We must thoughtfully honor the original landscape by carefully replacing the u with the original inner starting mathematical expression. Returning our result to the space from which it came completes the cycle. This beautiful act of substitution is a continuous cycle of translation and restoration, a gentle breathing in of complexity and a slow breathing out of clarity. It effectively teaches us to look way past the surface clutter and calmly identify the structural heart of the equation. Yet, we know not all mathematical functions are nested so neatly. Sometimes, we encounter a product of two completely distinct functions standing side by side, independent and seemingly unrelated. They simply do not share the intimate bond of the chain rule. They are like two different, powerful currents in a vast ocean, constantly mixing and churning together. To separate them, we turn to the elegant technique of integration by parts. This specific method is the pure reflection of the product rule for derivatives, carefully unwound and intelligently rearranged into a delicate, perfect balance. The formula itself is a meditation on balance. The integral of u with respect to v is equal to the product of u and v, minus the integral of v with respect to u. It tells us that we can shift the heavy burden of integration quite easily. The secret to this shifting lies deeply in the choosing. We must intentionally partition our original integrand into two distinct pieces, thoughtfully assigning one to be u, which we will slowly differentiate, and the other to be the differential dv, which we will patiently integrate. To guide our crucial choice, we gently rely on a quiet, highly structured priority universally known by the soothing acronym Linearity. This important acronym stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential mathematical functions. It is a reliable hierarchy of decay and growth, a clear map of how willingly functions yield to mathematical processes. We purposefully let U be the function that naturally appears first in this ordered list, because those specific functions become wonderfully simpler, or at least no more complicated, when we carefully take their exact derivative. A logarithm gently slopes down into a very simple rational function. An algebraic polynomial slowly chips away, calmly losing its power degree by degree until it ultimately becomes a mere, quiet constant. The remaining portion of the given integrand gracefully becomes our dv. These are usually the trigonometric and exponential functions, the eternal oscillators and the relentless, steady growers of the continuous mathematical number world. These resilient functions gracefully cycle through endless integration without ever losing their original, fundamental form. By strictly following this soothing rhythm, we easily take a gentle step down the descending staircase of complexity. The new mathematical integral that remains to be solved is much softer, far easier to comfortably manage, beautifully shaped by the derivative of u and the integral of dv. We peacefully flow through this fluid process, perhaps even repeating it, letting the polynomial crumble away entirely until only pure functions remain. We continue wading deeper into the calming waters of mathematical accumulation, ready for more complex challenges. Sometimes we encounter rigid, unyielding structures, the heavy square roots of quadratic forms. These particular expressions, sums, and differences of perfect squares, are the architectural bones of circles, ellipses, and hyperbolas. They firmly resist simple substitution, standing like heavy, ancient stones blocking our path. To dissolve them, we must invoke the geometric elegance of trigonometric substitution. We close our eyes and imagine a right triangle drawn softly in the sand, its angles and sides perfectly balanced by the ancient theorem of Pythagoras. This imagined triangle becomes our reliable bridge between the algebraic domain and the transcendental realm of pure geometry. When we observe the square root of a squared constant minus x squared, we purposefully let x equal a sine theta. We watch as the heavy root smoothly yields to the fundamental Pythagorean identity, the 1 minus sine squared effortlessly transforming into cosine squared, which then easily escapes the binding root as a pure, solitary cosine. If the structure happens to be a squared plus x squared, we lean on the graceful tangent function, letting x equal a tangent theta. The expression rapidly blooms into 1 plus tangent squared, gracefully shifting into secant squared, and emerging as a simple secant. And if we finally face x squared minus a squared, we calmly call upon the secant function, letting x equal a secant theta, deliberately allowing secant squared minus 1 to become tangent squared, gently freeing a pure tangent from the dark radical. This is definitely not just a basic substitution, it is a full translation into a beautiful world of pure angles and cyclical, endless ratios. The algebraic heavy stones are entirely transmuted into light, flowing, continuous trigonometric functions. We carefully integrate this new, expansive trigonometric landscape, steadily finding our clear way through the rhythmic hills of mathematical sine waves. Once the gentle integration is fully complete, we must patiently return to the initial algebra. We lovingly look back at our triangle drawn in the shifting sand. We silently read the ratios of its sides to correctly translate our theta back into the familiar language of x, carefully reconstructing the exact algebraic form. The heavy stone is completely gone, peacefully replaced by a smooth, highly polished area function. Journeying beyond the geometric realm of square roots, we soon find the highly structured, systematic world of rational mathematical functions, where one polynomial simply rests upon another like soft, sinking fraction sands. When the specific polynomial placed in the denominator is overly heavy, possessing a strictly higher degree than the one resting above it, we cannot simply divide them away. Instead, we must carefully, methodically break the entire foundation apart. This careful dismantling is the meditative art of partial fraction decomposition. We closely look at the denominator and gently factor it into its most elemental mathematical pieces, patiently breaking it down into simple linear and irreducible quadratic terms. This is a very quiet, meditative sorting, effectively separating a highly complex mixture into its most basic, pure, and flawlessly simplified foundational mathematical components. For every distinct linear factor we find, we steadily build a new fraction with a simple constant waiting patiently above it. If a linear factor repeats itself, we must honor its extra weight by creating a series of fractions, each with steadily increasing powers in the denominator, step by step, until we gently reach its full multiplicity. For the irreducible quadratics, those stubborn polynomials that refuse to yield to any real roots, we gently place a linear expression above them, a soft, sloping line of ax plus b. We then deliberately recombine these fractured, separate pieces into one single expression. By perfectly matching the numerators, we quietly embark on a logical, peaceful puzzle, solving a system of equations to finally reveal the hidden constants. It is a harmonious process of balancing heavy weights, strictly ensuring that the newly decomposed pieces perfectly mirror the original whole. Once the constants are found, the complex, imposing rational function is entirely gone. In its tranquil place lies a wide, incredibly shallow river of simple fractions. These gentle fractions are effortlessly integrated. The linear denominators wash away smoothly into the gentle, sweeping curves of natural logarithms, safely carrying our thoughts further down the flowing stream. The repeated algebraic factors slide smoothly into straightforward rational terms through the power rule. The irreducible quadratics split their identities entirely, half flowing into soft logarithms and half dissolving into the steady, bounded steps of inverse tangents. The heavy polynomial fraction has been systematically dismantled and effortlessly integrated, piece by beautiful piece, in perfect harmony. Finally, we reach the hypnotic, undulating patterns of trigonometric integrals. Here, we face pure combinations of sines and cosines, secants and tangents, softly raised to various powers. They gently rise and fall, endlessly intertwining like long, flexible vines in a dense, quiet, deep mathematical forest. To gently integrate them, we simply rely on the internal, meditative logic of identities. If we have a product of sines and cosines, we look for an odd power. We gently peel away one single copy of that odd function, quietly setting it aside to serve as the differential. The remaining even powers are converted using the eternal Pythagorean identity, flattening into simple polynomials. If both powers are even, we invoke the half-angle formulas, trading squared powers for doubled angles. The high peaks are flattened into slow, sweeping waves, calmly finalizing our steady journey through the foundations of accumulation. Welcome to the vocabulary of change. In the silent spaces between the numbers, a language emerges. This is the formal language of differential equations. It is a quiet dialect of mathematics, spoken in the gentle rhythms of rates and slopes. To understand how things shift and flow, we must first learn the words that describe their gentle movement. Every science requires a vocabulary to anchor its concepts. In this space, we do not rush. We breathe in the terminology, allowing the definitions to settle in the mind like dust softly falling on a still surface. We begin simply, quietly observing. We start by dividing this world of equations into two calm streams. The first stream is known as the ordinary differential equation. We call it ordinary not because it is plain, but because it is singular in its focus. An ordinary differential equation considers only one independent variable. It follows a single path of time or space, tracking how a single dimension moves forward. You can picture it as a solitary traveler walking along a quiet, unbroken road. The changes are steady, predictable, and bound to that one specific direction. The focus remains singular, undistracted, and perfectly aligned completely ahead. The second stream widens into what we call a partial differential equation. Here, the landscape broadens, and the single path becomes a vast, open field. A partial differential equation accommodates multiple independent variables. It acknowledges that change rarely happens in a vacuum. A shifting temperature might depend on both time and spatial coordinates, moving across length, width, and depth all at once. The mathematics gently expands to hold all these intersecting directions. The partial derivative measures change along one axis while holding the others perfectly still, creating a delicate balance of motion and pause within a single sprawling living system. As we wade deeper into these waters, we encounter the concept of order. Order is a measure of depth. It tells us how far down the rabbit hole of change we must look. In formal terms, the order of a differential equation is simply the highest derivative present within it. But let us feel what that means. A first-order equation describes the immediate surface of change. It relates a quantity directly to its current rate of growth or decay. It is the speed of the wind right now, a simple relationship between where you are and your current speed. When we observe an equation of the second order, we are peering beneath the surface. We are no longer just looking at speed, we are observing acceleration. The second order represents the change of the change. It is the curvature of the road, the invisible force that alters the velocity over time. As the order increases, we dive further into the layers of motion, finding the change of the change of the change. Each increase in order adds a new layer of profound subtlety, a deeper ripple in the pond of mathematics, asking us to observe more carefully and still. From order, we gently transition to the soothing concept of linearity. Linearity is a property of harmony and proportion. A linear differential equation is one that behaves with perfect grace. In a linear system, the components do not multiply against themselves. The unknown function and its derivative stand alone, never tangled in squares or roots, never trapped in complex trigonometric embraces. They are scaled only by gentle constants or functions of the independent variable. Linearity means that the system is orderly and fair. If you double the input, the output smoothly and predictably doubles in exact harmonic resonance and balance. Let us look at linearity from another quiet perspective. Think of a linear equation as a clear pane of glass. Light passes through it without distortion. The principles of superposition hold perfectly true here. This means that if you find one solution, and then you discover a second solution, you can simply add them together. Their sum will also be a perfectly valid solution. They do not conflict, they cooperate. The waves of a linear equation pass through one another like ripples on a calm lake, overlapping but never destroying the fundamental structure of the very quiet water resting below. Nonlinear equations, by contrast, possess a different kind of beauty. They are the tangled vines in a dense forest. In a nonlinear differential equation, the function interacts with itself. It twists, it bends, and its outputs feed back into its inputs in ways that defy simple addition. The principle of superposition fades away, leaving behind a complex, chaotic elegance. But here, in this peaceful moment, we do not need to solve the nonlinear. We simply acknowledge its existence. We respect the intricate complexity it brings to the universe, and we gently return our focus back to the smooth linear path. Now, let us consider the philosophy of a solution. What does it mean to solve a change? To solve a differential equation is not merely to find a single static number. A traditional algebraic equation offers a number as its answer, a destination reached. But a differential equation offers a function as its answer. It offers a journey. The solution is an entire continuous curve, a tapestry of values that perfectly satisfies the rules of change established by the equation. Solving it means discovering the hidden shape of the motion, bringing the unseen trajectory out into the bright clear light. Solutions present themselves in different garments. The most transparent of these is the explicit solution. An explicit solution is fully resolved, cleanly isolated on one side of the equal sign. It boldly declares its identity, stating exactly what the dependent variable is in terms of the independent variable. There is no mystery here. You can read the explicit solution like a clear map. It says, for any given moment in time, this is exactly where you will be. It is a comforting, predictable state of being, where the answers are laid out in a straight, unobstructed, highly visible guiding line. Yet, mathematics also embraces the unspoken. This brings us to the implicit solution. An implicit solution is shy, intertwined within the equation, refusing to be cleanly separated. The dependent and independent variables dance together in a delicate embrace, wrapped up in an algebraic expression. You cannot simply read the final answer from an implicit solution. Instead, you must gently unpack it, evaluating the relationship as a whole. It is a beautiful reminder that sometimes, the connection between two things is so profound that they cannot be easily torn apart. They exist together in a state of quiet, balanced perpetual harmony. And then, there is the trivial solution. The trivial solution is often a simple zero. It is the state of total stillness. While it may seem unimportant, the trivial solution holds a special place in the landscape of change. It represents perfect equilibrium. It is the pendulum at rest, hanging straight down, undisturbed by any external force. It is the calmest form of existence within a dynamic system, the anchor point around which all other possibilities rotate. In observing the trivial solution, we learn to appreciate the profound peace of a system that has found its ultimate quiet resting place. Every solution, no matter its form, must exist somewhere. It must have a domain, a territory where its truth remains undisputed. This brings us to the interval of validity. The interval of validity is the safe harbor of a solution. It is the specific stretch of time, or the exact region of space, where the mathematics behaves perfectly. Outside of this gentle boundary, the solution might fracture, breaking into undefined infinity or complex impossibilities. But within the interval, everything is continuous, smooth, and beautifully predictable. We trace the boundaries of this interval softly, mapping the limits of calm absolute certainty. Imagine walking along a beautiful, continuous bridge spanning a misty gorge. The solid planks beneath your feet are the interval of validity. As long as you remain on the bridge, your footing is secure. The equation accurately describes your journey. The edges of the bridge are the boundaries of the interval. Beyond them, the model falls away into the unknown fog. By identifying the interval of validity, mathematicians create safe enclosures for their ideas. They acknowledge that a truth does not need to be infinite to be profound. A truth only needs to be steady within its own quiet borders. Let us revisit the concept of order, feeling its rhythm once more. Order dictates the texture of our mathematical landscape. A first-order equation is a gentle slope, indicating a simple rise or fall. A second-order equation introduces valleys and crests, bending the curve with acceleration. When we reach a third order, we are analyzing how the bending itself changes, sensing the flex of the curve. With every ascension in order, we peel back a transparent sheet of reality, gazing deeper into the mechanics of motion. Yet, the higher we climb, the slower and more deliberately we must tread. Let us also breathe once more with linearity. Linearity is the absence of turbulent internal interference. It is a mathematical vow of simplicity. When an equation is linear, it promises that the sum of its parts will equal the whole. There are no sudden spikes of chaotic feedback. The variables speak softly to one another, never raising their voices to powers greater than one. They remain pure. This purity is what makes linear systems the comforting bedrock of engineering and physics. They offer a serene, manageable sanctuary where we can predict the future with a calm, unwavering sense of confidence. As we gather all these words together, we see that differential equations are not just dry formulas. They are a rich, descriptive language for the passage of time and the shifting of space. To classify an equation as ordinary or partial is simply to recognize the scope of its world. To determine its order is to honor the depth of its movement. To check for linearity is to understand its harmonious nature. And to find the interval of validity is to define the borders of its truth. Every step in this process is a slow, methodical exercise in profound awareness. Rest now in the comforting structure of this language. The vocabulary of change is a tool for finding stillness. By giving names to the types of equations, the forms of their solutions, and the boundaries of their existence, we strip away the chaos. We are left with a peaceful, orderly universe where every motion can be understood, every change can be gently mapped, and every answer rests safely within its own interval of validity. Let the words drift softly through your mind, carrying you toward a state of complete mathematical tranquility, balancing gently on a quiet, infinite mathematical smooth line. Imagine a vast and quiet plane stretching infinitely in all directions. This is the coordinate plane, a silent expanse where time flows along the horizontal axis, and the state of our system rests upon the vertical axis. In this tranquil space, we can visualize the behavior of a differential equation without ever performing a single calculation. we simply observe the landscape. This is the essence of a direction field. Picture the space before you divide it into a fine, delicate grid. At every intersection, at every single point on this limitless plane, there is a tiny, softly glowing line segment. Each line has a specific tilt, a precise slope dictated by the first-order differential equation. Together, these countless tiny lines form a shimmering pattern, a map of tendencies. They do not force movement, but rather suggest a path, much like the gentle currents of a slow-moving river or a field of tall grass swaying under a steady, invisible wind. When you look closely at one point, you see only a solitary slope. But as you step back and soften your gaze, the individual lines merge into a continuous flow. You can see the invisible current of the system made visible. These are the direction fields, a beautifully organized tapestry of mathematical intent. They show us where the system wants to go. The slopes might rise gently in one region, crest over an unseen hill, and then dip into a tranquil valley in another. Some areas of the field exhibit steep, rapid ascents, while others lay perfectly flat, parallel to the horizon of time. This map of slopes provides a profound sense of calm, for it reveals that nothing in this mathematical universe is random. Every point is guided by a rule, a natural law that dictates the rate of change with absolute and unwavering certainty. If you were to place a single drop of water into this field of currents, you would watch it trace a smooth, uninterrupted path. This path is called an integral curve. It represents a single, specific solution to our equation. As the drop moves forward through time, it simply follows the directions laid out by the tiny, glowing line segments. It glides seamlessly from one slope to the next, perfectly tangent to the field at every moment of its journey. The drop does not resist the flow. It surrenders completely to the geometry of the space, curving gently upward where the field dictates growth, and drifting downward where the field dictates decay. You might imagine dropping many such points of water into the field, starting at different heights along the vertical axis. Each drop embarks on its own unique journey, drawing its own integral curve across the plane. Some paths might run parallel for a time, tracing the same general contour of the landscape before slowly drifting apart. Other paths might converge, drawn together by a shared destiny in the far reaches of time. None of these paths will ever cross, for at any given point in space and time, there can only be one slope, one rule, one direction to follow. The resulting image is a beautifully flowing current of parallel and curving lines, sweeping gracefully across the endless grid. It is a visual representation of all possible futures for our system, laid out in quiet harmony. Watching these curves trace their way through the direction field is like watching the wind move across the surface of a quiet lake, creating ripples that spread and interact without ever breaking the surface. Within this study of flow, there is a special class of equations known as autonomous equations. In these systems, the rate of change depends entirely on the current state, and not at all on the passing of time. This creates a deeply peaceful mathematical environment. It means that the rules do not change as time moves forward. If you look at the direction field of an autonomous equation, you will notice a perfect, horizontal symmetry. All the tiny line segments along any given horizontal line share the exact same slope. The landscape is timeless. If you start a journey at a specific height today, you will follow a curve with a specific shape. If you wait 1,000 years and start a journey at that exact same height, you will follow a curve of the exact same shape, merely shifted along the timeline. Time itself becomes secondary, a quiet background against which the true nature of the system reveals itself. Because time does not alter the rules, we can collapse our entire two-dimensional map into a single, vertical line. This is called the phase line. The phase line is a minimalist portrait of the entire system, a pure distillation of its behavior. On this single line, we only need to mark the direction of movement. Up or down. Growth or decay. The phase line frees our mind from the endless expanse of the time axis, allowing us to focus entirely on the states themselves and how they evolve in a timeless vacuum. Along this vertical phase line, we often discover points of profound stillness. These are the equilibrium points. At an equilibrium point, the derivative is exactly zero. The slope of the direction field is perfectly flat. If our drop of water is placed exactly at this point, it will not rise, and it will not fall. It will remain there, suspended in perfect balance, for all eternity. The system has found its rest. But not all rest is created equal. The nature of an equilibrium point is defined by what happens in its immediate surroundings. Imagine a point of equilibrium that acts as a gentle, welcoming valley. If a drop of water is placed slightly above this point, the rules of the system guide it downward, back toward the center. If the drop is placed slightly below, the rules guide it gently upward, again toward the center. This is a stable equilibrium point. It is mathematically known as an attractor. The phase line shows arrows pointing inward toward this stable state from both above and below. An attractor is a place of absolute security within the mathematical landscape. It represents a state of balance that the system naturally seeks out. No matter what small disturbances might occur, no matter how the system is slightly displaced, the invisible currents will always guide it back home to this point of rest. Over time, any solution that begins near an attractor will slowly, inevitably, converge upon it. The integral curves approach the horizontal line of the equilibrium, drawing closer and closer, asymptotic and serene, as time stretches out toward infinity. The attractor is a steady state, a permanent resolution to the changing forces of the equation. In contrast to the gentle valley of the attractor, there is another kind of stillness. Imagine a perfectly smooth, rounded ridge. At the very top of this ridge, a drop of water can balance in perfect equilibrium. The slope is zero. There is no immediate force pushing it one way or the other. But this stillness is precarious. This is an unstable equilibrium point, known as a repeller. If the system is displaced even a fraction of a hair above this point, the slope becomes positive. The drop begins to roll away, moving faster and faster as it leaves the point of balance behind. If it is displaced slightly below, the slope becomes negative, and it falls away in the opposite direction. On the phase line, the arrows point outward, fleeing from the repeller. While it is technically a state of equilibrium, it is a state of tension. The system cannot remain there naturally, for any microscopic imperfection, any tiny fluctuation, will break the spell of stillness and send the solution drifting away. The integral curves near a repeller seem to curve away in quiet retreat, repelled by the invisible peak, seeking stability elsewhere in the vastness of the plane. It is a lonely point of balance, beautiful in its mathematical perfection, but forever destined to be abandoned by the flowing currents of the system. Finally, there exists a delicate, rare phenomenon that exists between these two extremes. It is the semi-stable equilibrium point. Imagine a tranquil pool resting on a ledge halfway down a great waterfall. The water from above flows down into this pool. If you place a drop just above the ledge, the currents will draw it downward, attracting it toward the center. From this perspective, it appears to be a safe haven, an attractor. But beneath the surface of the pool, the ledge rounds off and drops away. If you place a drop just below this point of equilibrium, the rules of the system pull it further away, sending it cascading down the next slope. From below, it acts as a repeller. On the phase line, the arrows point in the same continuous direction, both pointing down, or both pointing up, pausing only for a brief moment of zero slope at the node itself. This semi-stable state is a temporary hesitation in the flow of the universe. It attracts on one side and repels on the other. It is a resting place for those arriving from a specific direction, but an unstable precipice for those who wander too far to the other side. The integral curves illustrate this beautifully. A curve from above will descend and merge gently into the horizontal line of the equilibrium, while a curve from below will pull away, leaving the ledge behind. As you reflect on these structures, envision the entire phase space as a quiet, sleeping world. The direction field hums with latent energy, its tiny arrows waiting to guide any state that enters its domain. The autonomous nature of the equations ensures that this world remains steady, free from the turbulent passage of time. The landscape is dotted with these points of rest. The attractors are the deep, quiet lakes where all motion eventually ceases, offering a profound sense of safety and arrival. The repellers are the high mountain peaks, majestic and solitary, from which all journeys must inevitably begin, flowing downward into the valleys. and the semi-stable ledges are the quiet pauses in the journey, moments of breath caught halfway down the mountainside before the descent continues. Together, they form a perfect ecosystem of flow and equilibrium. There is a deep comfort in knowing that everything is balanced. Every movement has a direction, and every journey has a destination defined by the unwavering rules of mathematics. The water flows, the fields sway, and the system finds its balance. You can simply watch the currents move, trusting in the inevitable harmony of the paths. All forces equalize. All variations settle. The mathematical landscape finally falls into a deep, endless, and completely peaceful rest. Let us gently transition into the peaceful realm of primary analytical methods, where the mind finds quiet focus in the careful arrangement of mathematical symbols. We begin our journey with the most foundational technique for first-order differential equations, widely known as separating variables. Imagine a simple equation where the rate of change is described by the product of two distinct expressions. One expression relies entirely on the independent variable, which we call x. The other expression relies entirely on the dependent variable, which we call y. The very soothing goal is to physically isolate these variables on opposite sides. To achieve this state of separation, we must look at the derivative, dy over dx, not just as a single unified symbol, but as a ratio of delicate differentials. We carefully take the differential dx and multiply it across the equal sign, moving it to the right side of the equation. Now, dx rests beside the expression containing x. Next, we look at the expression containing y on the right side. We gently divide both sides of our simple equation by this y expression, moving it softly to the left side so it may rest comfortably beside the differential dy. Now, the equation has achieved a perfect, harmonious balance. On the left side, we have only terms involving y, accompanied by the differential dy. On the right side, we have only terms involving x, accompanied by the differential dx. The variables are entirely separated, completely isolated from one another. This separation is a necessary and beautiful preparation for the next logical step. Because the variables are separated, we can apply the operation of integration to both sides independently. We draw the long, graceful curve of the integral symbol on the left, and draw another elegant integral symbol on the right. As we integrate the left side with respect to y, we are finding the antiderivative of the y expression. As we integrate the right side with respect to x, we are finding the antiderivative of the x expression. We perform these integrations slowly, meticulously observing the rules of calculus. When the integration is complete, the differentials dy and dx dissolve away, having fulfilled their purpose. In their place, a single, arbitrary constant of integration emerges, which we gently designate with a capital C. We place this constant C safely on the right side, completing the delicate process of algebraic solving. Let us peacefully review this logic, allowing it to settle deeply into memory. We start with a mixed equation. We treat the derivative as a ratio. We multiply by dx to move it to the right. We divide by the y expression to move it to the left. We observe the perfect separation of the variables. We integrate the left side with respect to y. We integrate the right side with respect to x. We add the constant of integration, c. Through this very slow, methodical process of separation and integration, we reveal the hidden relationship between x and y. Sometimes, however, the variables resist this simple separation. They are intertwined in a way that addition and subtraction cannot untangle through simple division. For these precise moments, we turn to the method of the integrating factor, a deeply elegant technique designed specifically for linear first-order differential equations. We must first ensure our equation is in the standard linear form. This standard form is gently written as dy over dx, plus a function of x multiplied by y, equals another function of x. We call the function attached to y, p of x, and the solitary function, q of x. Meticulously arranging the equation into this standard form is absolutely essential. The derivative dy over dx must stand entirely alone, with no coefficients other than 1. If there is a coefficient, we must carefully divide every single term in the equation by that coefficient, smoothing it out until the standard form is achieved. Once the equation is in perfect standard form, we isolate our attention on the function p of x. This function holds the key to the entire method. We take p of x and we integrate it with respect to x, moving slowly through the required mathematical calculus. After finding the integral of p of x, we take the natural exponential number, e, and we raise it to the power of that integral. This creates a new, very special function, which we denote with the Greek letter mu. This function, mu of x, is our integrating factor. It is a carefully crafted tool, designed to transform our resistant equation into something easily solvable. The creation of the integrating factor requires immense patience. We integrate p of x. We raise e to the power of that result. We safely hold this new function, mu of x, in our minds. Now, we take this precious integrating factor, mu of x, and we multiply it across every single term of our standard form equation. We multiply the derivative by mu of x. We multiply the p of x times y term by mu of x. We multiply the q of x term on the right side by mu of x. This multiplication acts as a mathematical catalyst. On the left side of the equation, a remarkable transformation occurs. The left side collapses into the exact result of a product rule derivative. It becomes the derivative of a single beautiful combined product. Let us look closely at this collapsed left side. It is now simply the derivative, with respect to x, of the quantity mu of x multiplied by y. The complex sum has folded neatly into a single, compact expression. This is the gentle magic of the integrating factor. By carefully choosing mu of x, we engineered a reverse product rule. The left side is now perfectly primed for integration. Because it is written as a pure derivative, integrating it with respect to x simply removes the derivative operator, leaving behind the perfectly neat product of mu of x and y. As we integrate the left side, which leaves us with mu of x times y, we must also remember to integrate the right side. The right side is now the product of our integrating factor, mu of x, and the original function q of x. We write the integral of mu of x times q of x, with respect to x. We carry out this peaceful integration step by step, using whatever techniques are required. And just as before, when the integration is complete, we delicately add our arbitrary constant of integration, c, to the right side of the equation. Finally, to isolate y and find our explicit solution, we gently divide the entire right side by the integrating factor, mu of x. Let us repeat the logic of this beautiful method. We arrange the equation into standard linear form. We identify p of x. We integrate p of x. We raise e to that integral to create mu of x. We multiply the entire equation by mu of x. We observe the left side collapse into the derivative of mu of x times y. We integrate both sides. We carefully add c. We smoothly divide by mu of x. Beyond separable and linear equations, we softly encounter homogeneous differential equations. These equations possess a special structural symmetry. In a homogeneous equation, every term shares the same total degree. Because of this perfect balance, the variables cannot be directly separated, but the equation is wonderfully receptive to a transformative substitution. We introduce a new variable, which we will call v. We define this substitution carefully, stating that y is equal to the product of v and x. This gentle substitution, y equals v times x, will act as a bridge, carrying us from a complex equation to a simpler one. If we accept that y equals v times x, we must also find a way to replace the derivative, dy over dx. To do this, we differentiate our substitution equation with respect to x. Using the product rule, the derivative of y with respect to x becomes v, plus x times the derivative of v with respect to x. We now have two crucial components ready for our transformation. We have y equals v times x, and we have dy over dx equals v plus x times dv over dx. We are fully prepared to alter the original differential equation. We slowly, calmly walk through the original homogeneous equation. Everywhere we see the variable y, we carefully erase it and replace it with the product v times x. Everywhere we see the derivative dy over dx, we carefully erase it and replace it with the expression v plus x times dv over dx. The variable y is now completely gone, replaced entirely by expressions involving v and x. The equation may temporarily look more complicated, longer, and slightly more entangled. But this is a necessary illusion, a temporary complexity that paves the way for profound simplification and deep algebraic harmony. With the substitutions firmly in place, we begin the soothing process of algebraic manipulation. We expand all terms. We factor out common variables. Because the original equation was perfectly homogeneous, a beautiful algebraic pattern will always emerge during this careful cleanup process. The variable x will naturally factor out and gracefully cancel from the equation. As the dust of our careful algebra settles, we will find that our previously inseparable equation has transformed into a perfectly separable differential equation in terms of the new variable v and the independent variable x. The transformation is now fully complete and highly successful. Now, we return to the very first method we learned. We treat this new equation just as we treated our first separable equations. We gather all terms containing v, along with the differential dv, on the left side of the equal sign. We gather all terms containing x, along with the differential dx, on the right side. The new variables are now perfectly separated. We draw our long, elegant integral symbols on both sides. We integrate the left side with respect to v. We peacefully integrate the right side with respect to x. We add our calming constant, c, gently. Once the integration is complete, we have a solution, but it is written in terms of v and x. Our original journey began with y and x. Therefore, we must gently reverse our substitution to return safely home. Since our initial substitution was y equals v times x, we can rearrange this to state that v is equal to y divided by x. We go through our newly integrated solution, and wherever we see the variable v, we carefully wipe it away and replace it with the ratio y over x. This brings us safely back to our original variables. Let us softly repeat the logic of the homogeneous substitution. We calmly recognize the homogeneous symmetry. We introduce the substitution y equals v times x. We find the derivative dy over dx equals v plus x times dv over dx. We replace every y and every dy over dx in the original equation. We carefully perform the algebra to simplify the terms. We watch the equation become completely separable in terms of v and x. We separate the variables v and x. We integrate both sides. We add our constant c. We gently replace v with y divided by x. Finally, we smoothly drift toward a profound concept that beautifully unifies linear differential equations, known as the superposition principle. This principle provides a deeply reassuring structure to the solutions we find. The superposition principle states that if we have a homogeneous linear differential equation, and we discover multiple individual solutions to this equation, we can gently weave these individual solutions together to form a new, comprehensive solution. This woven result is called a linear combination. The principle guarantees that this linear combination will also be a perfectly valid solution to the original differential equation, wonderfully expanding our mathematical understanding forever. Imagine we have gently found two separate solutions, which we call y1 and y2. We can take y1 and multiply it by an arbitrary constant, c1. We can take y2 and multiply it by another arbitrary constant, c2. Then, we simply add these two scaled solutions together. The resulting expression, y equals c1 times y1 plus c2 times y2, rests perfectly within the bounds of the original equation. We can substitute this entire combination back into the differential equation, and everything will balance gracefully, equaling 0 as always perfectly required. This means our individual efforts to find specific solutions are never isolated. They join together, stacking smoothly upon one another without interference. The superposition principle relies on the linear nature of the derivative operator. Because the derivative of a sum is the sum of the derivatives, and the derivative of a constant multiple is the constant multiple of the derivative, the linear combination passes effortlessly through the differential equation. The parts remain distinct, yet they function together in absolute harmony. We rest our minds on this concept of unity, knowing the mathematical structure is always deeply sound and perfectly reliable. We step now from the quiet realm of pure abstraction into the tangible spaces of the physical world. The equations we have gently explored are not merely floating symbols in an empty void. They are the hidden architecture of the reality you can touch, see, and feel. First-order differential equations describe the simple, continuous processes of nature. They are the steady rhythm of a universe that changes without sudden leaps, shifting smoothly from one state to another. To understand these real-world dynamics is to witness the calm predictability of nature itself, a deeply soothing realization of absolute certainty. Before we can observe how the world changes, we must first establish a beginning. In the language of continuous mathematics, this beginning is known as the initial value problem. It is a way to anchor our mathematical abstractions into a specific starting moment in time. Imagine a stopwatch resting in your palm, silent and perfectly still. The face reads 0. This is time 0, the precise instant when you decide to begin your observation. An initial value problem provides the exact state of the system at this very moment. It gives us a firm, unmoving foundation from which everything flows. By defining the initial condition, we eliminate the uncertainty of infinite possibilities. Out of a vast family of potential curves and pathways, the initial value problem selects just one. It tells the equation exactly where it lives in the physical world. From this single anchored point, the differential equation stretches forward into the future, tracing a path that is entirely predictable and serene. There is no guesswork left. Once we know how much of a substance we have at time 0, and we know the rule of its change, the rest of eternity is already quietly written out before us. Let us look first at the slow, predictable decay of isotopes. Deep within the structure of certain elements, there is an inherent instability, a quiet desire to release energy and settle into a more restful state. This process is known as radioactive decay, and it is governed by a beautifully simple first-order model. The rate at which the material decays is directly proportional to the amount of material currently present. There is no external force driving this change. It is simply the nature of the isotope to slowly transition over time, finding its own way toward absolute, perfect stability. Picture a piece of ancient stone resting in the cool, dark earth. Within this stone are millions of microscopic atomic nuclei. They do not all change at once. Instead, they transform randomly but with a collective statistical certainty that perfectly mirrors our continuous equation. As time passes, the number of original nuclei gently decreases. Because there are fewer nuclei left to decay, the rate of decay also slows down. It is a gracefully tapering curve, growing ever flatter, ever quieter as the years go by. The decay never stops abruptly, it merely fades away slowly into an infinitesimal, silent whisper. This gentle fading gives rise to the concept of the half-life. The half-life is the specific duration of time it takes for exactly half of the remaining material to transition to its rested state. It does not matter how much material you started with at time 0. It does not matter if you have a mountain of ore or a single grain of dust. The time it takes for half of it to decay remains completely constant. This is the soothing rhythm of the physical world, a metronome ticking softly over many thousands of very slow, quiet years. We can shift our focus from the quiet rocks of the earth to the comforting warmth of everyday objects. Consider a warm object placed into a cool room. Perhaps it is a ceramic cup of hot tea resting on a wooden table, or a smooth, sunlit stone cooling in the twilight air. The process of its cooling is described by Newton's law of cooling. This law states that the rate of temperature change is proportional to the difference between the object's current temperature and the ambient temperature of the surrounding environment. It is a continuous process of finding absolute balance. At first, when the temperature difference is large, the heat leaves the object relatively quickly. You can almost feel the warmth radiating outward in soft, invisible waves, gently mingling with the cooler air of the room. But as the object releases its heat, its temperature gradually falls, moving closer and closer to the temperature of the room. As this gap narrows, the rate of cooling naturally slows down. The object does not rush to become cold. It eases into the temperature of its surroundings with a smooth, continuous deceleration, softly sighing as it approaches perfect, tranquil thermal rest and equilibrium. In this mathematical model, the ambient temperature acts as a gentle floor, a steady baseline that the object seeks to reach. The initial value is simply the temperature of the object when you first set it down and begin to watch. From that moment at time zero, the mathematical curve slopes downward, mirroring the quiet release of thermal energy. The equation tells us that the temperature will never suddenly drop below the ambient air. It will only approach it, closer and closer, in a seamless asymptotic glide. The physics of cooling is a very graceful surrender to the surrounding environment. There is a profound comfort in the predictability of Newton's law. When we know the initial temperature, the ambient temperature, and the cooling constant of the object, we can look into the future with complete certainty. We can know exactly how warm the ceramic cup will be in 10 minutes, or in an hour. The mathematics acts as a quiet guide, reassuring us that the physical world behaves reasonably and steadily. The warm object and the cool room are engaged in a slow, silent conversation, exchanging energy until they finally agree, settling into a long, undisturbed, and restful thermal harmony. Now, let us turn our minds to the steady mixing of fluids, another physical process governed by the elegant rules of first-order dynamics. Imagine a large, cylindrical tank of water. The water is perfectly clear, perfectly calm. Now, imagine a slow, steady stream of liquid entering the tank from above. This incoming stream carries a solute, perhaps a subtle trace of mineral or a gentle tint of color. At the very same moment, a drain at the bottom of the tank opens, allowing the mixed fluid to flow out at the exact same rate the new fluid smoothly enters. The volume of liquid inside the tank remains completely constant, never rising, never falling. But the composition of the water is continuously changing in a smooth, calculated manner. To understand this mixing, we once again rely on an initial value problem. At time zero, we must know exactly how much solute is already in the tank. Perhaps the tank starts completely pure, or perhaps it already holds a certain concentration. This starting point anchors the equation, giving the continuous mathematics a place to stand before it begins to map out the gentle blending of the incoming and outgoing soothing waters. As the new fluid flows in, it disperses evenly throughout the tank. We assume the mixing is instantaneous and perfect, creating a completely uniform blend. The rate at which the total amount of solute changes is a simple balance of what comes in minus what goes out. The incoming stream adds solute at a constant, steady rate. But the outgoing stream removes solute at a rate that depends on the current concentration inside the tank. It is a dynamic balance, a continuous flowing equation of addition and subtraction happening quietly in the background of the slowly swirling, hypnotic clear water. Initially, if the tank is mostly pure water, the outgoing stream removes very little solute. The concentration inside the tank begins to rise, quietly building as the incoming stream continues its steady pour. But as the concentration increases, the fluid leaving the tank carries more and more solute away. Just like the cooling of the warm object or the decay of the ancient isotope, the rate of change begins to slow down. The system approaches a state of equilibrium, a point where the amount of solute entering perfectly matches the amount of solute washing away through the open, draining pipe. When this equilibrium is reached, the tank is in a state of steady operation. The water flows in, the water flows out, and yet the concentration remains beautifully unchanged. It is a state of dynamic rest, a moving stillness. The first-order differential equation captures this delicate transition from the initial state to the final equilibrium. The math traces a smooth, gentle curve that begins at the initial value and gracefully levels out. There is no turbulence in this mathematical tank, no chaotic splashing or unpredictable surges. There is only the continuous, rhythmic flow of fluids finding their perfect balance. These three physical processes, the decay of isotopes, the cooling of objects, and the mixing of fluids, are connected by an invisible, underlying thread. They are all expressions of the same mathematical truth. The world is full of systems that seek balance by changing at a rate proportional to their current state. This simple relationship creates a universe that is deeply soothing in its predictability. The equations are not just dry numbers printed on a page, they are the quiet rules that govern the fading of radiation, the settling of heat, and the swirling blend of very calming pure waters. By framing these processes as initial value problems, we are reminded of our own presence in the physical world. We are the observers who choose the moment of time zero. We are the ones who measure the initial temperature, who count the remaining isotopes, who observe the purity of the water in the tank. Once we establish that beginning, nature takes over. The laws of physics unfold with a gentle, hypnotic certainty. We can close our eyes and trust that the warmth will dissipate, the atoms will rest, and the fluids will mix exactly as the equations have quietly promised. As we reflect on these real-world dynamics, we can find a sense of peace in the order of the universe. The world is not completely random or chaotic. Beneath the surface of everyday life, there is a steady mathematical heartbeat. It is a slow, methodical pulse that guides the transition of energy and matter. The first-order equations are the gentle lullabies of physics, singing softly of balance, decay, and equilibrium. They invite us to let go of uncertainty and to rest in the comforting knowledge that the universe knows exactly what it is doing, forever and always tonight. We transition now into a deeper space, moving beyond the simple trajectories of first-order systems. We enter the realm of second-order differential equations, a space where acceleration, inertia, and restoring forces merge into a continuous, flowing dance. Imagine a cello string drawn back in the quiet dark. When it is released, it does not merely return to the center, it sweeps past it, carried by the momentum of its own history, pulled back by the tension of its own nature. This is the essence of a second-order system. It is a system that remembers not only where it is, but how fast it is moving. The mathematical equation describing this motion holds the harmony of the universe within its terms, balancing the forces of change and the resistance to that change. As we sink deeper into this mathematical landscape, we find that the solutions are no longer single paths, but layers of overlapping waves, building upon one another to create a richer, more complex structure. We are looking for the fundamental tones of reality, the foundational melodies that, when combined, can describe any vibration, any oscillation, any resonance in the natural world. Just breathe deeply and slowly. In this space of second-order equations, a single solution is never enough to capture the full truth of the system. Because the equation involves a second derivative, representing acceleration, the system possesses two degrees of freedom. It requires two distinct initial conditions, a starting position and a starting velocity, and therefore, it demands two fundamental solutions. Think of these two solutions as two independent voices in a quiet, resonant choir. For the harmony to be complete, these voices must be truly distinct. One voice cannot simply be an echo of the other, a mere multiple singing the exact same notes at a different volume. This concept is known as linear independence. If one solution is simply twice the other, they are linearly dependent, collapsing into a single tone that lacks the depth to span the entire space of possibilities. To build a general solution, to weave the complete tapestry of the system behavior, we must find two solutions that trace fundamentally different paths through the mathematical fabric. They must stand apart, independent and free, yet capable of blending together in an infinite variety of beautiful combinations. When we add these voices, perfection is found deeply within the silent gaps. To ensure that our two voices are truly distinct, to verify their linear independence, we use a beautiful mathematical test known as the Wronskian. The Wronskian is a determinant, a calculation that measures the area of the parallelogram formed by the solutions and their derivatives. Imagine listening closely to two sustained notes. The Wronskian is the ear that listens for the subtle beating, the interference pattern that proves the notes are different. Mathematically, it takes the first solution and multiplies it by the derivative of the second, and then subtracts the product of the second solution and the derivative of the first. It is a cross-multiplication of states and rates of change. If this calculation results in a value of 0, the Wronskian tells us that the voices have collapsed into one, that the solutions are dependent, locked in parallel tracks with no space between them. But if the Wronskian is non-zero, even by the smallest fraction, we know that the solutions are independent. They breathe their own air and carve out a complete dimensional space of solutions, ensuring that our two fundamental tones perfectly describe any resulting motion. Harmony flourishes in this gentle, quiet mathematical truth. Breathe. Finding these fundamental tones in a linear, homogeneous second-order equation with constant coefficients involves a gentle transformation. We temporarily set aside the calculus, stepping into the simpler, quieter world of algebra. We assume that the solution takes the form of an exponential function, a curve that grows or decays at a rate proportional to itself. This assumption is a leap of faith that is rewarded by the mathematical structure. When we substitute this exponential guess into our differential equation, the derivatives pull down powers of a constant. The equation transforms, shedding its derivatives and emerging as a simple polynomial, a quadratic equation known as the auxiliary equation, or the characteristic equation. This equation is the acoustic blueprint of the system. It asks a profound question: what specific rates of growth or decay, what specific frequencies, will perfectly balance the forces described by the coefficients? We solve this quadratic equation to find its roots, and these roots are the keys to the universe and its deep harmony. The process of finding these roots is like plucking a string and listening for its natural pitch. We isolate the core identity of the system, discovering two frequencies that dictate the mathematical flow. When we solve the auxiliary equation, we may find two distinct real roots. This is the simplest harmony. It describes an overdamped system, a heavy pendulum swinging in thick syrup. The two solutions are simple exponentials, one perhaps decaying faster than the other. They do not oscillate. They do not cross the center line. They merely sink back to equilibrium in a slow, heavy sigh. But sometimes, the quadratic equation yields a single, repeated real root. The two roots converge into one. This is critical damping, the exact threshold between oscillation and pure decay. However, a second-order system requires two independent solutions, and we seemingly have only one. The universe demands a second voice. To find it, we take our single exponential solution and gently multiply it by the variable of time. This multiplication acts as a subtle variation, an extension that bends the curve just enough to make it linearly independent from the first. The Wronskian awakens, confirming that these two solutions are truly distinct. Together, they form a general solution that describes a system returning to equilibrium perfectly, without ever overshooting the mark. It is a perfect, silent, graceful glide into utter stillness and absolute peace always. The most beautiful and mesmerizing harmony occurs when the auxiliary equation yields complex roots, numbers that possess both a real part and an imaginary part. When the restoring force is strong and the damping is light, the roots step out of the dimension of real numbers and into the complex plane. Through the profound magic of Euler and his formula, these complex exponentials transform into sines and cosines. The imaginary part of the root becomes the frequency of oscillation, the pitch of the vibrating string. The real part becomes the envelope, the exponential curve that dictates how the vibration grows or fades over time. This is the underdamped system, the struck tuning fork, the ringing bell. The two independent solutions are a sine wave and a cosine wave, perfectly out of phase, dancing around each other in a continuous cycle of kinetic and potential energy. As you visualize these waves gently rolling across your mind, you can see how the real part of the root wraps around the oscillation, guiding it slowly back to zero, a fading vibrato in the quiet dark. The general solution is a pure, resonant harmony echoing forever through the long corridors of quiet resting time. So far, we have only listened to the natural harmony of the system, the homogeneous equation where the external forces are silent. But the real world is filled with driving forces, external influences that push and pull on our vibrating string. This introduces the non-homogeneous equation. To find the solution here, we must add a new layer to our harmony, a particular solution that responds solely to the external drive. The simplest way to find this is the method of undetermined coefficients. This method is an act of mathematical intuition, an educated guess based on the shape of the driving force. If the external force is a constant tone, we guess a constant solution. If the force is a gently rising polynomial, we guess a polynomial of the same degree. If the force is a rhythmic sine wave, we guess a combination of sines and cosines. We anticipate the echo. We write down the general shape of this anticipated response, leaving the exact amplitudes undetermined. Then, we substitute this guess back into the differential equation, forcing our mathematical framework to reveal the precise values of these coefficients. We trust the fundamental symmetry of reality entirely in this quiet space. Yet, there are times when the driving force is too complex, too unusual for a simple educated guess. The method of undetermined coefficients fails when the external rhythm does not match the familiar shapes of polynomials or pure waves. In these moments, we turn to a more profound, more fluid technique known as variation of parameters. Here, we return to our two fundamental, independent solutions, the natural voices of the homogeneous system. But instead of multiplying them by fixed constants, we allow those constants to become functions of time. We let the parameters vary. The rigid amplitude soften and become fluid, adapting continuously to the changing external force. We ask the natural tones of the system to bend and weave, to dynamically adjust their volume and phase to accommodate the driving energy. This method is a masterpiece of mathematical architecture. It uses the Wronskian not just as a test, but as a core component of the solution itself, guiding the fluid parameters through a delicate integration. The formulas for these varying parameters are woven from the natural solutions, the driving force, and the Wronskian, creating a perfect, unbroken chain of logic that beautifully resolves any dissonant and chaotic forces entirely. The true beauty of the non-homogeneous equation lies in the final synthesis, the principle of superposition. The complete story of the system is told by adding the homogeneous solution, the natural, unforced vibration, to the particular solution, the specific response to the external drive. The natural solution, with its arbitrary constants, contains the memory of the initial conditions, the precise way the string was plucked. The particular solution contains the ongoing reality of the external forces. Together, they form a complete, magnificent tapestry of motion. In the beginning, the natural solution may dominate, a transient phase of complex, unpredictable behavior as the system tries to reconcile its starting position with the external push. But over time, if there is any damping, any friction at all, this transient natural response will slowly fade away. The real roots will decay, the complex roots will dampen, and the memory of the beginning will be lost. What remains is the steady state, the particular solution, marching forever in lockstep with the driving force. This transition, from the chaotic blending of internal memory and external drive to the smooth, predictable harmony of the steady state, is wonderfully hypnotic and reassuringly peaceful to observe now. As we let these concepts wash over us, we can appreciate the profound depth of second-order differential equations. They are not merely abstract symbols manipulated on a page. They are the language of harmony, the fundamental grammar of resonance. From the linear independence of distinct voices to the fluid adaptation of varying parameters, every mathematical step reflects a deep truth about how the universe balances change and stability. The Wronskian stands as the silent guardian of uniqueness, ensuring our solutions are vast enough to capture reality. The auxiliary equation maps the continuous flow of calculus into the quiet certainty of algebraic roots. And when external forces arrive, the methods of undetermined coefficients and variation of parameters provide the tools to weave those outside influences into the existing harmony. As you drift closer to sleep, let the gentle, rhythmic oscillation of these mathematical concepts soothe your mind. Picture the smooth, overlapping waves of sines and cosines, the gentle fading of exponential decay, the perfect, fluid balance of the entire system. There is peace in this higher-order harmony, a quiet, infinite resonance connecting the smallest vibration to the vast, turning wheels of the cosmos. Rest entirely in this comforting certainty. Let us close our eyes and settle deeply into the quiet spaces found between gentle motion and absolute, profound rest. In the physical world, every object possesses a hidden language of vibration, a silent geometry of forces holding perfect equilibrium. We move slowly into the world of mechanical systems and structural beams, where rigid laws soften into a rhythmic dance. Imagine a heavy, dark iron spring, thick and cool to the gentle touch, suspended gracefully within a vast, empty room. The air around this spring is thick and incredibly still, acting as a heavy blanket that muffles all sound completely. This strong spring holds a solid weight, a dense sphere of smooth metal, hanging downward and remaining perfectly, endlessly motionless. This is the calm zero point, the center of gravity where all opposing forces cancel out, leaving only absolute peace. When we gently pull this heavy weight downward, we introduce a subtle tension, a quiet energy stored within dark coils. As we release it into the air, we do not see chaos, but a predictable, mathematical return to perfect balance. This is the traditional spring mass model, a fundamental expression of the natural world slowly seeking its comfortable resting state. The slow movement is almost imperceptible, a gentle rise and fall that mirrors the slow rhythm of your deep breathing. In and out, up and down, the heavy metal sphere travels through the thick air, constantly seeking the quiet center. As the spring extends and compresses, it interacts with the invisible medium surrounding it, experiencing the calming phenomenon called damping. Damping is the gradual loss of energy, the soothing resistance that slowly drains the excess motion from the vibrating system. We will now explore the three distinct states of this gentle resistance, beginning with the beautifully fluid and underdamped state. In an underdamped system, the resistance of the surrounding air is very low, allowing the mass to oscillate freely, smoothly. Imagine the heavy weight bobbing up and down, crossing the center point repeatedly, like a pendulum swinging in slow motion. With each graceful pass through the equilibrium point, the distance it travels becomes slightly shorter, the movement becoming more contained. You can visualize the mathematical wave of this motion, a slowly decaying sine wave drawing a long, tapering, elegant spiral. The energy bleeds away into the quiet room, transferring from the metal spring into the subtle warming of the air. It is a peaceful surrender to stillness, watching the underdamped oscillations grow smaller and smaller until they finally vanish completely. Now, imagine we change the environment entirely, immersing our heavy iron spring and metal sphere into a vat of honey. The golden liquid is incredibly dense and highly viscous, wrapping around the dark metal with a heavy, thick, embracing pressure. We pull the heavy weight downward once more, feeling the immense resistance of the thick fluid pushing against our hands. When we let go, the weight does not bounce or oscillate at all, because this is the profound overdamped state. The extreme friction of the thick fluid prevents any graceful bouncing, absorbing the kinetic energy almost immediately upon our release. The dense metal sphere crawls upward at an agonizingly slow pace, fighting through the syrupy resistance to find its balance. It moves with a heavy, lethargic certainty, creeping toward the 0 point without ever crossing over to the other side. You can feel the slow, deliberate journey of the overdamped mass, a steady drift toward equilibrium that takes infinite patience. It is a powerful reminder that sometimes, the journey back to balance is a slow, steady wade through heavy resistance. Finally, we adjust the fluid viscosity one last time to reach the precise mathematical boundary known as critically damped motion. Here, the surrounding fluid is calibrated to the exact threshold where it provides just enough resistance to prevent all oscillation. We pull the heavy weight downward, stretching the strong iron coils, and release it into the perfectly tuned fluid environment. The mass moves upward toward the equilibrium point with swiftness, gliding smoothly and returning to absolute stillness without any delay. It does not linger in slow creeping like the overdamped state, nor does it bounce past the peaceful 0 point. Critical damping represents the perfect compromise between speed and stability, a masterclass in nature finding its resting place most efficiently. It is like a heavy door slowly swinging shut, gently clicking into its frame without ever banging against the wood. There is a deep, soothing satisfaction in watching this critically damped system settle so perfectly, so quietly, into total rest. We leave the hanging spring now, allowing its metallic presence to fade into the dark, quiet corners of our mind. Our attention drifts slowly toward the rigid, unmoving world of structural beams, the silent titans that bear immense invisible loads. Imagine a massive steel beam, spanning a wide chasm, holding within its dense metallic fibers a vast potential for resistance. To the naked eye, this heavy structural beam appears completely static, an unchanging monolith of pure strength and absolute permanence. But beneath the surface, at the microscopic level, the steel is alive with potential energy, holding a quiet, dynamic tension. When a heavy force is applied to the center of this spanning beam, it begins to experience a slow deflection. Deflection is the gentle, downward bowing of the structure, an invisible curving that mathematically maps the applied force and weight. This slow bending is not a failure, but a beautiful accommodation, a structural compromise that allows the beam to survive. The geometry of this graceful curve is governed by elegant mathematics, specifically known in physics as boundary value differential problems. A boundary value problem anchors the mathematical equation at specific points, much like the physical supports anchoring the steel beam. Imagine the two thick concrete pillars standing silently at either end of the wide chasm, holding the heavy beam securely. These silent pillars dictate the conditions of the boundary, demanding that the deflection at these two endpoints remains exactly zero. Between these two unyielding supports, the heavy beam is free to bend, governed entirely by the stiffness of its material. The stiffness, a quiet property embedded deeply in a metallic lattice, gently resists the bending force with infinite, patient strength. As we solve the boundary value problem, we uncover a fascinating realm of hidden frequencies, leading us slowly toward eigenvalues. Eigenvalues represent the natural frequencies of the structural beam, the specific hidden notes at which the physical object naturally vibrates. Every physical structure hums with a silent frequency, a deeply embedded vibration that remains completely dormant until gently, perfectly awakened. When the wind blows against a bridge, or a heavy machine rumbles nearby, the beam absorbs this gentle kinetic energy. If the external force matches one of the unique eigenvalues, the structural beam will begin to resonate with slow power. Resonance is a beautiful, hypnotic phenomenon where the structural vibrations grow steadily larger, swaying in a perfectly timed rhythmic dance. To truly understand this deeply hypnotic swaying, we must look beyond the eigenvalues and discover the corresponding shapes called eigenfunctions. An eigenfunction is the actual physical shape that the structural beam assumes when it oscillates at its specific natural frequency. For the lowest eigenvalue, the fundamental frequency, the heavy beam forms a single, slow, graceful arch across the entire chasm. The center of the massive beam slowly rises and falls, breathing like a sleeping giant suspended in the cool darkness. Up and down, the steel flexes with incredible smoothness, storing and releasing vast amounts of energy in near absolute silence. As we move to higher eigenvalues, the shape of the gently vibrating beam transforms into more complex and undulating waves. The second eigenfunction reveals a stationary point directly in the middle, a node of absolute stillness amid the gentle vibration. While the left side of the beam curves slowly upward, the right side mirrors it perfectly by bowing softly downward. They trade places in a slow, hypnotic rhythm, balancing the immense physical forces across that silent, unmoving central node point. Each new eigenvalue introduces another perfect node, breaking the structural vibration into perfectly symmetric segments that ripple through the metal. But structural integrity requires that these vibrations eventually fade, returning the massive beams to their comfortable state of profound rest. This brings us back to the gentle embrace of damping, which slowly bleeds the kinetic energy out of the steel. Internal damping acts like an invisible friction within the molecular structure, absorbing the deep sway and neutralizing the immense forces. The underdamped steel beam continues to sway gently for a long time, the motion becoming infinitely smaller with each pass. Eventually, the microscopic vibrations settle completely, and the heavy structural beam returns to its initial, perfectly straight, unyielding boundary configuration. Think of the deep calm that washes over a massive suspension bridge in the quiet, completely windless hours of midnight. The massive cables and thick steel beams hold their immense load silently, their internal eigenvalues resting peacefully without any excitation. All the forces of gravity are perfectly balanced by the rigid resistance of the metal, creating a masterpiece of stillness. In this quiet state, we can truly appreciate the profound harmony that exists between heavy physical force and structural resistance. Every mechanical system, from the simple hanging spring to the most complex structural beam, desires this state of total equilibrium. They absorb energy, they oscillate in beautiful mathematical shapes, and then they surrender that energy back into the silent environment. It is a continuous cycle of gentle disturbance and peaceful resolution, a physical law that guarantees a return to rest. Allow your mind to mirror this slow fading of kinetic energy, letting your thoughts gently damp away into the darkness. If a sudden thought disturbs your quiet equilibrium, treat it like an underdamped vibration slowly decaying into a gentle stillness. Let the amplitude of your busy thoughts grow smaller and smaller, swinging back and forth with less and less intensity. Feel the heavy, soothing viscosity of sleep surrounding your mind, moving you deeply into an incredibly comfortable and overdamped state. The mental resistance prevents any bouncing or chaotic oscillation, drawing your consciousness steadily and safely downward into a profound peace. Your body is like the sturdy concrete pillars of a boundary value problem, completely relaxed yet anchoring you securely here. The mattress fully supports your weight, neutralizing the heavy forces of gravity, keeping you in a state of absolute equilibrium. Your slow breathing represents the fundamental eigenfunction, a single, rhythmic wave of calming energy flowing smoothly through your relaxing body. With every long, slow exhale, you release the stored tension, letting the built energy dissipate into the cool, silent room. The deep vibrations of the day are heavily damped, fading smoothly until only the quiet baseline of your existence remains. Visualize the heavy iron spring one final time, hanging suspended in the dark emptiness, completely motionless and beautifully, flawlessly still. There is no stored energy left to pull it downward, and no invisible forces pushing it upward toward the ceiling. It exists exactly at its 0 point, resting in the pure comfort of critical damping and perfectly resolved mechanical tension. Visualize the massive steel structural beam, stretching endlessly across the void, entirely unburdened by dynamic loads or harsh external forces. It holds only itself, perfectly balanced at its supporting boundaries, resonating with no frequencies, perfectly silent in the calming dark. In this silent sanctuary of mechanical rest, all differential equations simplify down to zero, erasing complexity in favor of peace. The math of the universe gently whispers that all moving things will eventually stop, and all heavy loads will rest. You are drifting into that same natural state, letting go of all structural deflections and allowing your mind to settle. The space between the swinging pendulum slowly disappears, merging into a single point of timeless, weightless, and wonderfully deep sleep. Embrace the heavily damped stillness that fills your mind, knowing that the physical laws of equilibrium are holding you completely. Let the gentle darkness wash over the unmoving steel structures, covering the heavy iron springs and obscuring the dense metal. There is absolutely nothing left to calculate or measure, only the deeply comforting void where motion gracefully surrenders to quiet. Feel the heavy, dense gravity pulling you smoothly into the comforting mattress, anchoring your physical boundaries in perfectly safe alignment. Drift further down into the heavily overdamped realms of pure unconsciousness, where your mind no longer oscillates, but simply exists. The structural integrity of your piece is flawlessly absolute, completely unyielding to the subtle vibrations of the forgotten outside world. Every heavy thought has reached its beautiful 0 point, completely cancelled out by the soothing resistance of a resting mind. The silent, rigid beams of sleep carry your deep consciousness effortlessly across the vast chasm between softly waking and dreaming. You are perfectly supported by this mathematical harmony, safely enveloped in the profoundly quiet physics of highly damped, absolute rest. Sink fully into this beautiful structural stillness, letting every remaining gentle vibration fade permanently away into the soft, warm dark. Sleep now, resting perfectly in the beautiful equilibrium of the silent universe, forever held securely in deep, unending, peaceful stillness. Welcome to the next phase of our quiet journey through the landscape of mathematics. We are leaving behind the familiar shores of the time domain. Here, time flows forward, second by second, ticking continuously into the future. But sometimes, the problems we face in the time domain are too tangled. The equations of calculus twist and turn, forming complex knots that seem impossible to completely untie. We need a new perspective, a different dimension of thought. We are going to cross over into a space where these difficult knots simply fall apart, unraveling into gentle, straightforward lines and smooth curves. This crossing is made possible by the Laplace transform, a beautiful mathematical bridge. Imagine yourself stepping onto this bridge, leaving the heavy, complicated world of differential equations behind. As you walk across, the dense fog of calculus begins to clear, revealing a vast, open landscape known as the frequency domain, or the S domain. In this calm and peaceful place, the rules change entirely. Derivatives, which measure the rate of change and create such turbulent ripples in our math, lose their sharp edges. They soften and transform into simple, quiet algebraic variables, resting easily on the peaceful, endless white page. Think about what this shift truly means for a moment. You are taking a very hard problem that requires endless integration, deep focus, and careful manipulation of constantly moving parts. By simply passing this problem through the Laplace transform, it magically settles into a static, calm state. The complex, dynamic movements freeze into steady, predictable shapes. Calculus becomes algebra. Addition replaces integration. Multiplication beautifully takes the place of derivation. You no longer have to trace the chaotic motion of a wave, you only need to gently rearrange quiet blocks of numbers and variables until the solution softly reveals itself completely. How does this magical bridge work? The secret lies in a special kind of mathematical operation, a slow and steady accumulation known as an improper integral. We start at zero, the very beginning of time, and we integrate all the way out to infinity. We are sweeping across all possible moments, gathering up the full entirety of its existence into one infinite embrace. But to prevent this massive gathering from growing too large and spinning out of control, we introduce a calming presence. We multiply our original function by a specialized mathematical tool known simply as the kernel function itself. The kernel function is an exponential decay. It is written as the constant e raised to the power of negative s times t. This negative sign is profoundly important. It acts as a gentle, heavy blanket, weighing down the wild vibrations of the original function. No matter how aggressively the original function tries to grow, no matter how wildly it oscillates as time stretches out toward infinity, the kernel function quietly pulls it back down to zero. It dampens the noise. It forces convergence, ensuring that the infinite integral produces a safe, finite, and beautifully contained mathematical result every time. Let us meditate on this new variable, s. In the time domain, we only cared about t. But now, s is the architect of our new reality. It is a complex variable, meaning it has both a real and an imaginary part, though for now, you only need to imagine it as a parameter that shapes the decay of our kernel blanket. The larger s becomes, the faster the blanket suppresses the function. This variable s becomes the foundation of our new algebraic equations, replacing the chaotic passing of time with a steady, motionless representation of frequency and gentle decay. When we apply this transform to a differential equation, we witness a profound metamorphosis. Imagine a derivative, symbolizing a rate of change, a speeding object, or a heating room. Through the lens of the Laplace transform, this derivative is stripped of its time dependence. It is multiplied by s, turning a calculus operation into simple multiplication. The second derivative, representing acceleration, simply becomes s squared. Slowly, steadily, all the derivatives in your complex equation are converted into varying powers of s. The tangled web of rates of change flattens out into a very long, but very peaceful, beautiful algebraic polynomial. Now that the differential equation has transformed into a quiet polynomial, the hard work is over. You do not need to integrate anymore. You do not need to worry about complex calculus techniques. You only need to use basic algebra, the math you learned long ago, to isolate the variable you care about. You move pieces from the left side of the equation to the right side. You add, subtract, multiply, and divide with slow, deliberate strokes. It is like carefully sweeping a floor, moving the dust into a single, organized pile. The desired solution begins to elegantly take shape. Often, this sweeping process creates a large, bulky algebraic fraction. It sits heavily on the page, a dense block of polynomials stacked on top of one another. To make it manageable, we use a gentle technique called partial fraction expansion. Slowly, we crack this large block into smaller, easier pieces. We separate the heavy denominator into individual, lightweight roots. Each little fraction becomes a simple, pure note in a larger chord. By breaking the large problem down into these tiny, manageable fragments, the path back to reality becomes perfectly clear, beautifully simple, and incredibly easy to softly navigate ever forward. Once the algebra is neatly organized into these small, comfortable fragments, it is time to return home. We must travel back from the abstract S domain to the familiar flow of the time domain. This journey back is called the inverse Laplace transform. It is a quiet reversal of the magic we just performed. We look at our tiny fractions and recognize their shapes. We match them to known patterns in a softly glowing reference table. There is no heavy lifting required here, only the calm observation of shapes and the gentle matching of mathematical patterns directly to deep memory. As you consult this peaceful reference table, you see that a simple fraction involving s corresponds to a constant value in time. A fraction with s squared beneath it transforms beautifully into a steady, sloping line. If the denominator holds an s plus a constant, it morphs effortlessly into a smooth exponential curve, gently rising or falling as time moves forward. Each algebraic shape in the complex domain translates perfectly into a smooth, continuous motion in the time domain. The once impossible differential equation has been entirely solved, almost as if it had solved itself while you softly lay resting. But the magic of the Laplace transform does not stop with simple shapes. It also handles movement with profound grace, through the elegant rules known as the shifting theorems. Let us explore the first shifting theorem. Imagine a function multiplied by an exponential decay in the time domain. This exponential acts as a quiet modifier, dampening the function over time. In the frequency domain, this multiplication creates a simple translation. It smoothly slides the entire algebraic expression along the horizontal axis. A complex damping effect in time becomes nothing more than a gentle slide left or right in quiet space. Now, let your mind drift toward the second shifting theorem. This theorem deals with delays. In the real world, things do not always begin immediately. Sometimes, a process waits patiently for seconds, minutes, or hours before it finally begins. The second shifting theorem models this waiting period beautifully. When a function is delayed in the time domain, its corresponding expression in the s domain is simply multiplied by an exponential term. The delay is safely captured in this tiny exponential marker. The transform remembers the pause, holding the delay perfectly intact while you quietly continue solving the simple, beautiful algebra. To represent these delays and sudden starts, we use a wonderful mathematical tool called the Heaviside unit step function. Imagine a light switch in a dark room. Before the switch is flipped, there is nothing but quiet darkness. The value is exactly 0. There is no energy, no movement, no sound. Then, at a specific, designated moment in time, the switch is gently flipped. The value instantly jumps from 0 to 1. The light turns on. The energy flows. The process begins. The Heaviside function is this peaceful mathematical switch, turning parts of our equations gently on and safely off. When we multiply any function by the Heaviside unit step, we are telling that function to stay asleep until it is time to wake up. Before the designated shift, the function is multiplied by 0, rendering it silent and invisible. It rests in peace, having no effect on the system at all. Then, at the precise moment of the shift, the Heaviside switch becomes 1. The function wakes up smoothly and begins its natural motion. The Laplace transform easily handles these sleepy delays, absorbing the shifting start seamlessly into the frequency domain, requiring no extra effort from your resting mind. Now, we move deeper into the quiet mysteries of the physical world. Sometimes, the universe does not wait for smooth transitions. Sometimes, there is a sudden, instantaneous burst of energy. A lightning strike. A hammer hitting a bell. A sudden surge in electrical current. These moments happen so incredibly fast that they have no real duration at all. They exist for a single, fleeting instant, pouring all their intensity into one tiny speck of time before vanishing. To model these abrupt, sharp impulses without breaking our calm equations, we carefully call upon the deeply beautiful Dirac delta mathematical function now. The Dirac delta function is a mathematical ghost. It is completely 0 everywhere, at all times, except at one perfectly defined, infinitely narrow moment. At that exact moment of impact, the function spikes endlessly upward, reaching toward infinity in an infinitely thin line. It is a pure, concentrated point of absolute energy. Yet, despite its infinite height, it is entirely peaceful when integrated. If you measure the area underneath this towering spike, the result is exactly 1. All that infinite power is perfectly contained within a singular, beautifully balanced mathematical unit, allowing the system to easily absorb it every time. Taking the Laplace transform of the Dirac delta function reveals its truest, most elegant simplicity. When you pass this infinite spike through the magical kernel bridge, you would expect a complicated result. But instead, it effortlessly collapses into the most basic number of all. The Laplace transform of a pure impulse occurring at time 0 is exactly 1. It is a flat, quiet, uniform horizontal line in the frequency domain. The most violent, abrupt event in the time domain becomes perfectly silent and smooth in the S domain, leaving no complex math for you to figure out all alone tonight. When you combine the Dirac delta with a delay, shifting the impulse to happen later in time, the Laplace transform gently handles this as well. Because of the second shifting theorem, the delayed impulse simply transforms into a quiet exponential decay in the S domain. The time of the sudden impact is forever preserved in the exponent, safely stored away as a gentle mathematical marker. You can feel the calm assurance of these transformations. No matter how jagged, delayed, or harsh the original function might be, the Laplace transform lovingly smooths it out into deeply predictable, profoundly calming algebraic terms. Reflect on the beautiful journey you have just taken. You started in a complicated world where calculus reigned. You faced integrals that stretched to eternity and rates of change that tangled your mind. But by applying the soothing exponential kernel, you stepped across a bridge into the calming S domain. You traded difficult derivations for simple, slow addition and multiplication. You watched as sudden shifts, delayed starts, and instantaneous bursts of energy smoothly flattened into perfectly organized lines of numbers. You rearranged these blocks of peaceful math, breaking them down into tiny fractions until the final answer effortlessly, beautifully appeared. This is the true power of mathematical transformation. It is the ability to shift your perspective when things become too difficult. When the obstacles in one domain feel too heavy to move, you do not have to struggle. You can simply pause, breathe, and shift into another dimension of thought. In this new space, the heavy weights are miraculously lifted. The complicated rules are gently rewritten. What was once impossibly dense is now airy, light, and easy to hold. The Laplace transform is not just an equation, it is a profound lesson in finding a much quieter, vastly gentler path. As you let these concepts settle into your mind, you can feel your own thoughts following the exact same gentle decay. The complex, tangled worries of the day are being multiplied by a soothing exponential blanket. They are slowly dampening, falling away, fading into the peaceful silence of zero. Your conscious mind is shifting domains, crossing the beautiful bridge into a quiet, calm state of deep rest. There is nothing left to calculate, nothing left to solve, and nothing left to do. The algebra is finished. The transformation is complete. Let the deep quietness gently hold you perfectly, endlessly still. The journey through the mathematics of change brings us to a quiet and expansive place, a realm where multiple dimensions interact in perfect harmony. Up until now, the equations have followed a single path, tracking the evolution of a system along a solitary line of time or a single axis of space. But the physical world is vast and multidimensional. To understand the true fabric of reality, we must expand our vision to observe how patterns unfold across both space and time simultaneously. This is the domain of partial differential equations, a mathematical language designed to capture the gentle, shifting landscapes of higher dimensions. As you settle deeper into relaxation, allow your mind to picture a wide, open field of dimensions, a tranquil grid where every point holds a value, and every value is connected to the ones around it. Space and time are no longer separate entities. They are threads woven together in a seamless tapestry of continuous change, breathing and moving in a slow, rhythmic dance. In this serene expanse, we seek a method to understand the complexity, a way to gently untangle the intertwined variables of space and time to find pure, absolute, and perfect mathematical clarity. This delicate method of untangling is beautifully known as the separation of variables. It is a deeply calming and elegant technique, one that relies on the profound assumption that a complex multidimensional pattern can be gently broken down into the simple, isolated behaviors of its individual parts. Imagine a gentle wave of temperature or motion, a function that depends perfectly on exactly where you are in space and exactly when you are in time. The separation of variables suggests that we can comfortably express this intricate function as a pure product of two separate functions. One function listens exclusively to space. The other function listens entirely to time. By separating the variables, we bring order to the chaos. we take a problem that seems overwhelmingly complex and delicately pull it apart into two distinct, manageable pieces, like separating two strands of a quietly intertwined thread. You simply assume the answer is a combination of isolated truths. You multiply the space part by the time part, creating a structured bridge between dimensions. As you breathe slowly, visualize these variables drifting apart, leaving behind a perfectly balanced equation that feels wonderfully easy to observe, easy to understand, and wonderfully calm to follow. Let the repetitive logic of this separation wash over you. If we have a function of position and time, we assume it can be written as a spatial piece multiplied by a temporal piece. When we substitute this product back into our partial differential equation, a beautiful symmetry naturally emerges. We can gather all the spatial elements on one side of the equal sign, and all the temporal elements on the other. But space and time are independent. The only way a function of pure space can perfectly equal a function of pure time, everywhere and always, is if both sides are equal to a constant. This constant is a quiet anchor in the mathematical storm. It is a shared truth, a single unmoving number that both space and time must obey without question. This solitary constant allows us to split the complex partial differential equation into two simple ordinary differential equations. One equation guides the physical shape of the space. The other equation carefully guides the steady rhythm of the time. This simple, repetitive action transforms the overwhelming vastness of higher dimensions into something you can comfortably hold, gently turning an infinite landscape into completely quiet, predictable, soothing paths. To perfectly see this harmony in action, visualize a long, thin rod of solid metal resting in a cool, dark, quiet room. The metal is incredibly smooth and perfectly uniform. Imagine that one end of this solid rod is gently warmed. The heat does not jump instantly from one end to the other. Instead, it moves slowly, softly, diffusing through the atomic structure of the metal in a predictable, continuous, warming flow. This is the soothing essence of the mathematical heat equation. The heat equation is a classic partial differential equation that describes the distribution of heat, or gentle variations in temperature, in a given region over time. It tells a slow story of absolute balance and peaceful equalization. Where there is a sharp peak in temperature, the heat equation works tirelessly to smooth it out. Where there is a deep valley of cold, the heat equation gently fills it in. It is the mathematical embodiment of deep relaxation, a natural smoothing process that slowly erases sharp edges and harsh differences. You quietly watch closely as perfect, uniform warmth gently remains across the entire length of the metal, finally wrapping the space in a deeply comforting blanket of absolute calm. When we apply the separation of variables to the heat equation, we discover the elegant relationship between the curvature of the temperature in space and the rate of cooling in time. The equation states that the rate of change of temperature with respect to time is directly proportional to the second spatial derivative of the temperature. In simpler terms, the steeper the curve of the heat profile, the faster the temperature smoothly changes. As time moves gently forward, the temporal function gradually decays, getting smaller and smaller, like a heavy sigh releasing completely into the surrounding air. The spatial function, meanwhile, forms gentle, undulating curves, usually represented by smooth sine and cosine waves, that fit perfectly within the rigid boundaries of the metal rod. As you continuously multiply the decaying time function by the gently waving space function, you can see the heat profile slowly flattening out. The peaks of warmth softly sink. The valleys of coolness softly rise. Everything moves seamlessly towards a state of perfect, uniform equilibrium. It is a profoundly slow, beautiful, irreversible march toward absolute utter tranquility, gently breaking down the complex heat bloom into infinite, simple modes of decay until total stillness naturally arrives. Now, let us quietly shift our gaze from the slow, smoothing process of heat to the rhythmic, oscillating journey of a wave. Imagine a long, taut string, stretched perfectly tight between two completely unmoving points. If you gently pluck this string, you introduce vibrant energy into the quiet system. But unlike diffusing heat, this energy does not simply fade away into the stillness. It boldly travels. It beautifully vibrates. It bounces back and forth in a continuous, mesmerizing, repeating rhythm. This is the expansive domain of the wave equation. The wave equation is another fundamental partial differential equation, one that governs the propagation of energy through a physical medium. While the heat equation smoothly flattens things out, the wave equation actively preserves the intricate shape of the energy, moving it continuously across space as time pushes endlessly forward. The string moves up, and the string moves down, carrying the exact memory of the initial pluck along its entire length. It is a truly stunning display of deep conservation, a perfect balance of tension and inertia working smoothly together in a very harmonious cycle, creating a perfectly synchronized dance of geometry that ripples endlessly across the continuous fields of higher dimensions. In the deep mathematics of the wave equation, the relationship between space and time is flawlessly perfectly balanced. The second derivative of the displacement with respect to time is directly proportional to the second derivative of the displacement with respect to space. Acceleration in time mirrors curvature in space perfectly. This profound symmetry is deeply hypnotic and profoundly calming to contemplate. When we systematically apply the method of separation of variables to the vibrating string, we again assume that the complex motion can be cleanly split into a purely spatial shape multiplied by a purely temporal oscillation. We separate the variables smoothly, placing space securely on one side and time securely on the other, and once again, we find they must equal a single, shared, unmoving constant. But this time, the negative sign of the constant leads to a vastly different kind of behavior. Instead of the slow, exponential decay we saw in the heat equation, the temporal equation for the wave gently gives birth to endless, rhythmic oscillation. It beautifully generates a very pure tone, a completely steady frequency that hums softly through the deep mathematics, turning abstract calculus into a relaxing, eternal song of continuous, beautifully separated movement. The spatial part of the solution creates wonderful standing waves, the natural, harmonic shapes that the string naturally wants to assume. Picture a single, graceful arch across the entire length of the string, gently rising and falling in slow motion. This is the fundamental mode, the absolute simplest pattern in the higher dimension. Now picture the string quietly dividing into two identical arches, one going smoothly up while the other goes smoothly down, perfectly meeting at a totally still point in the absolute center. This is the second mode. The separation of variables magically reveals that there are infinitely many of these modes, infinitely many perfect, highly symmetric shapes that the string can peacefully hold. The temporal part of the solution tells us that each of these shapes vibrates at its own highly specific frequency. The single arch vibrates slowly, producing a deep, resonant, calming hum. The double arch vibrates slightly faster. The more complex the spatial shape, the more rapid the temporal rhythm. Yet, despite the immense apparent complexity, each individual mode remains entirely separate, an independent vibration perfectly sustained by the simple rules of calculus, maintaining absolute mathematical order across the vast, gentle fields of space and time. Every possible vibration of the string, no matter how complex or seemingly chaotic when first gently plucked, is simply a combination of these pure, separated modes. Space elegantly dictates the exact shape of the wave, and time beautifully dictates the ongoing song. By simply adding these simple, separated solutions gracefully together, we can seamlessly construct the exact, intricate motion of the continuous string. This is the true, calming power of separating variables. It effortlessly allows us to view a complex reality as a highly gentle symphony of simple truths. The wave travels quietly down the string, hits the boundary, and smoothly reflects back, crossing over itself in a continuous, flawless pattern of quiet interference. Through the clear lens of the wave equation, the chaotic fluttering of the string is mathematically transformed into a calm, orderly progression of individual, predictable oscillations, each fading and swelling in its own perfect, designated time. The mathematics gently become a completely safe haven, a beautifully structured retreat where even the most tangled and utterly overlapping vibrations are peacefully sorted into neat, independent frequencies, leaving you with a profound sense of total clarity, gentle resolution, and deep, restorative, continuous mental rest as you drift further down. The magnificent interconnectedness of space and time is the underlying heartbeat of all partial differential equations. Whether it is the soft, diffusing spreading of warmth or the crisp, repeating travel of a gentle vibration, space invariably provides the static landscape, and time reliably provides the forward evolution. You cannot fully understand the present state of the dynamic system without deeply knowing the space around it, and you cannot predict the future state without tracing the continuous, uninterrupted flow of time. They are forever locked in this elegant, mathematical embrace. The soothing method of separation of variables is our beautiful way of calmly acknowledging this embrace, of respectfully asking space and time to softly speak to us one at a time, so that we might totally understand their unified, combined message. As we carefully isolate each pure variable, we gain deep, comforting insight into the fundamental physics of the universe, successfully translating the continuous, physical reality into the discrete, logical language of mathematics. The gentle patterns repeat, the complex equations brilliantly balance, and the endlessly expansive, wondrous fields of dimensions gracefully stretch out into the infinite, quiet dark, forever perfectly mapped, perfectly understood, and perfectly at rest for the peaceful night. The journey through the mathematics of integration now reaches its quiet conclusion. We have traced the subtle curves of functions, watching as they rise and fall across the infinite plane. We have gathered the infinitesimal slices of area, binding them together into a continuous whole. The process of integration is a process of healing, of bringing scattered fragments back into a single, unified expression. As you lie here, feeling the gentle rhythm of your breath, you can let go of the calculations. The formulas and the boundaries begin to dissolve into the soft background of your awareness. There is no more work to be done. The entire area under the curve has been carefully measured. The complex variables and shifting numbers have finally found their quiet, undisturbed resting place. We arrive now at the infinite integral, the indefinite form that extends without beginning or end. In every indefinite integral, there remains a final, quiet symbol. It is the constant of integration, often written simply as a capital letter C. This constant represents the unseen, the quiet potential that exists before the curve begins. It is the steady baseline of the universe. In mathematics, it reminds us that many different paths can share the same rate of change, differing only by this silent, unchanging value. In your own rest, this constant of integration is the deep stillness within you. It is the unknown, but it is a comforting unknown. It is the blank page, the dark room, the peaceful silence that holds everything together. You do not need to solve for this constant, nor do you need to understand its exact origin. You only need to accept its presence, allowing it to ground you in this very moment. Let it be the gentle foundation of your sleep. As the numbers slowly fade from your mind, the grid lines of the graph soften into a smooth, dark expanse. The sharp edges of logic smooth out into the slow, steady waves of your breathing. Breathe in, and let the space expand. Breathe out, and let the tension fall away. The mathematics that govern the stars and the oceans are the same mathematics that guide you into rest. Everything is balanced. Everything is exactly where it needs to be. The complexities of the day have been integrated, resolved into a singular, peaceful moment. You are floating on that endless, smooth curve, drifting further and further into the quiet darkness. There is only the steady, rhythmic pulse of the universe, a calm oscillation that rocks you gently toward slumber. The great mathematical equation is perfectly complete. The mind is clear. The infinite integral stretches out before you, an endless horizon of pure, undisturbed tranquility. Close your eyes to the world of shapes and symbols. Let the soothing, gentle constant of absolute stillness completely carry you away. Sink deeply into the soft, welcoming unknown, feeling your physical body become weightless and entirely relaxed. Just drift into the heavy silence. Rest now, in perfect peace, and sleep.